the topics of the exercises in the exercise sheet for this week. So which are the first, I'll be talking about evolution of the Gaussian wave packet. Then I'll be talking about the notions of group velocity and phase velocity. And finally, we'll be looking at the topic that you already had in the lecture, which concerns the double slit experiment, and we'll be looking at how we can measure in the double slit experiment. So find out which is the slit the electron or the particle went through in the experiment. Okay, so let us start. So we start with the evolution of the Gaussian. So we're back to, or maybe not so favorite, Gaussian wave packet. And the idea is that we were looking previously at just, so let us plot the Gaussian. So here we have it, it's peaked around x0. Suppose now we were looking at different properties of the Gaussian, like, for example, how does it look in momentum representation? What is the expectation value of the position and momentum, and so on. And now we'll be looking at how the Gaussian wave packet evolves under the free particle Hamiltonian. So we'll look at the evolution and apply it for time t. So after mt, and I'll give you the spoiler, the Gaussian packet evolved under the free particle Hamiltonian, still stays a Gaussian wave packet. It will probably become a bit more wide, it will spread a bit, but it will still stay a Gaussian wave packet. It's going to be like peaked around some x prime. And the idea of this exercise is that we need to find what is exactly what is exactly the shape of this Gaussian, like what is its spread, and what are the expectation values of the position and momentum. Okay, so at time t equals 0, we start with already the formula that we've seen before. So it's just a Gaussian, which is peaked, a Gaussian wave packet, which is peaked around x0. And the momentum of the Gaussian wave packet is k, hk. So this we've already seen before. Okay, and the evolution, we want to look at the evolution with the following Hamiltonian, h, which is a free particle Hamiltonian, which is just p squared over 2 mu, where mu is the mass of the particle. And let me first can propose a roadmap to how we will like the least painfully come to our final conclusion about how the wave function will look like after evolving under this Hamiltonian for time t. So what we can notice about this Hamiltonian is that it is the function of p, of the operator p. And what we also know about the operator p is that if we act with the operator p in the momentum representation of the wave function, then essentially its action can be trivially described as just multiplying by p as a momentum value. So then we can say that since h is a function of the operator p, then it is easier to see how it is applied to psi in terms of momentum representation. Okay, so for this, what we can do is we can take our initial Gaussian at time t0, and then find how its representation in momentum, in terms of momentum. So psi bar of p and 0. And for this, we only need to do a Fourier transform. And then we can evolve the wave function in the momentum representation, which for this Hamiltonian will be a very easy application. And then what we will arrive to after evolving it for time t, we will get psi bar of pt. And then to get back to the position representation, we just have to perform an inverse Fourier transform to arrive back to our position representation. And then we will look at the psi of xt modulus squared, and we'll see that, as I said, spoilers, it's a Gaussian. And finally, then we will compute the the expectation value of the momentum at time of the position at time t, and also of the momentum. Okay, so let us start. So the first step here is to go from, for time equals 0, to go from the position representation into the momentum representation. This is something that we already done. Just for your knowledge, it's exercise sheet 4, I think, exercise 3, where you had to find the momentum representation of the Gaussian wave packet. And so I will not do the Fourier transform here. I'm just copying the result from what we got back then. So it's psi bar of p0. We also remember that the Fourier transform of the Gaussian is also Gaussian because it's a nice function. Maybe not so nice to integrate, but the properties are nice. So for the momentum, we essentially have a Gaussian, which is peaked around p equals hk. Okay, so our first step is done. Next step is to understand how does psi bar of p0 evolve under free particle Hamiltonian, which is p squared over 2 mu. Well, from the Schrödinger equation, we know that the evolution under this Hamiltonian corresponds to the following unitary: u of t, which is e to the power minus I h t over h bar. Then we do here what we usually do, we just write it as series. 1 over n factorial minus it over 2 mu h. I already substituted instead of h, p squared over 2 mu to the power n. And then here we have p squared to the power n. So p squared to the power n is just p to the power 2n. Okay, so now let us act with this unitary on our state psi. And then since we want to know how it acts for the momentum representation, then we just add the bra p here. So this is for momentum representation. Okay, so then we just substitute u with the expression above. Just writing it here. P to the power 2n psi. Okay, since P is the eigenoperator of the bra state P, we know how it acts. So it's just this just gives us the eigenvalue of the P, which is just the value of the momentum P to the power 2n. P stays here. Okay. Then we take the sum out because it's just the coefficients. Here we act with P to the power 2n on the bra P as indicated above. And here, so we get just value of momentum P to the power 2n, get P psi. Okay, so the first part of the expression is just the definition of the exponential, where we get e to the power minus it p squared over 2 mu h. And p psi is just the wave function in the momentum representation. So psi bar of p0. Okay, so our conclusion is as follows. How does psi bar of p0 evolve under this Hamiltonian? Well, it takes our psi bar of p0 to just psi bar of p0 multiplied by this exponential. And this we will call psi bar pt. Okay, so we arrived to how our Gaussian wave packet looks like after time t in the momentum representation. The next step is, well, we need to go from this momentum representation to the position representation, which means that we just have to perform an inverse Fourier transform. Okay, then this is what we do. So we have psi of xt 1 over 2 square root of 2 pi h bar psi of bar of pt e to the power, e to the power ipx over h bar dp, integrating from minus infinity to plus infinity. And we can make one remark here is, well, are we justified in saying that our psi x of t is indeed the solution to the Schrödinger equation for the evolution of the Gaussian under the free particle Hamiltonian? Well, it is because psi bar of pt is the solution to the Schrödinger equation in the momentum representation, which means that if we come back to the position representation, then psi of xt would also trivially be representing a solution of the Schrödinger equation in the position basis. Okay, so now we just have to calculate this. So we first insert what psi bar of pt is, which is psi bar of p0 e to the power minus it p squared over 2 mu h bar. Then we have another exponential here. And then finally we insert the definition of psi bar of p0, which is, let me see it, coefficient. Yeah, so square 2 sigma squared over pi h squared, yeah. Then the exponential goes, of course, inside. Yeah, so then we have here the exponential minus p to the minus p minus h bar k squared, sigma squared over h bar squared. Yeah, let me put all the others in the exponential as well. So plus I p minus hk, or is it minus here? Yeah, sorry, it's minus I p minus hk x0 over h bar minus it p squared over 2 mu h bar plus ipx over h bar dp. Okay, so I will not calculate this integral here because first I think I already took number of integrals of this type. So the idea here is first that you go from p, from the variable p to p minus hk. And then you have some expression in the exponential. And there you have to take out the full square. So it would be like something p minus something squared something plus some leftover stuff. So you have to put like everything that goes with p in this like in this square, and then the leftover stuff just goes out of the integral because it doesn't depend on p, and then this part of the integral is just the usual integral of the Gaussian with some coefficient. Also, just I wanted to make this remark is that like you're not required to, so this is not calculus, there's not a calculus class. So you for example in the exam you will not be required to take like one of these integrals. It's nice to know how to take them, but you can also, it's totally valid if you want to use Mathematica with them. Maybe it's nice to remember that, for example, oh, the Fourier transform of the Gaussian will be a Gaussian, just for estimating how the physical situation looks like. But again, like if you make some like some mistake in a coefficient or so, it's not a problem. Okay, so let's suppose that we did our painful integration either by hand or by typing it all in Mathematica. And what we arrived to is the following. Squared square root of pi over sigma squared over h bar squared plus it 2 mu h. Then we have the exponential, which is minus x0 minus hkt over mu squared over 4 sigma squared plus 2 it h bar over mu. And the last term is e to the power ikx minus it over h bar squared k squared over 2 mu. Okay. So finally we arrived to how our Gaussian wave packet looks like in the position representation after evolving for a time t under free particle Hamiltonian. Okay, so yeah, we can write that this we arrive to psi of xt. And we can also trivially see that, oh, it's also Gaussian because of this term here. It's also a Gaussian wave packet, which is actually still moving with the wave vector k. So yeah, so another yeah, you can to plot it depending on x, to plot this probability density psi of xt a modulus squared. This will be a Gaussian. However, like even without calculating stuff here, even without like explicitly calculating the mean value of x and the mean value of p at time t, we can actually already see what these values are just from the shape of the function. So we have psi of xt. Let's ignore some coefficients that are here, and let us just take this part. Copy, paste, and let us take the next part here. Oh, you even copied with the thing. Oh, no worries. Yeah, so we have these things. Did it go over something? Okay, sorry. Yeah, I think it was a fail, so I'll just rewrite this. So we have here, what we have here is the exponential of x minus x0 minus hkt over mu squared, and here we have something by e to the power ikx minus it over h squared k squared over 2 mu. So remember when we were looking at the expectation value of just the Gaussian here, psi x0, and the expectation value of the position was exactly x0. So this is something that appeared here. So it would be x minus x0, and in the end, the x0 would come out as the position expectation. Or here we can also kind of predict that. Okay, so if we have this Gaussian, which includes this exponential, and in the exponential, the nominator includes this, so it's like x is shifted by x0 plus hkt over mu. Then we can actually already predict that for the expectation value of x, so for the peak of the Gaussian, we would have x0 plus hkt over mu. And the same can be done for momentum. So we know that, for example, at the time t0, the expectation value of the momentum was hk. And at time t, we still, so for the momentum, we are orienting ourselves for this term here, e to the power ikx. And the k still, and the k there still stays the same. So essentially, it means that the momentum, the expectation value of the momentum doesn't change. So it's still hk, which physically also makes sense, because if it is a free particle Hamiltonian, then it means that there's kind of no energy coming in from the outside, which would kind of increase the kinetic energy of the particle. So essentially that means that gives us already the intuition that the momentum of the particle, because of the conservation of momentum, should not change. Okay. What else can be said? Maybe another remark is that, so we were looking here only at the nominator. So in denominator here, this value will determine how like how the spread of the Gaussian is behaving. So essentially, we see from here that this denominator value is 4 sigma squared plus 2I th bar over mu. And if we take the psi x of t squared modulus and plot it, then we'll see that the denominator of the Gaussian will be like 4 sigma squared plus like something like t squared h squared over mu squared. And this means that kind of the width of the Gaussian is increasing with time t. So essentially what happens is that, yes, if we start with this Gaussian at x0, then after time t, it will indeed move along the x-axis to x0 plus hkt over mu. But it will also become less peaked. So become like this, spread it. So this is, let's say, after time t. Okay, and so this is our conclusion about how the Gaussian wave packet evolves after time t. Okay, so this was the first exercise. Yeah, I think that was more or less it, except for the like calculation of the psi of xt modulus squared, which the hint is given in the exercise, and yeah, I think it's fairly straightforward calculation, already given the psi x of t. Yeah, in principle, when calculating the expectation values of x and p, you can just do the hand-wavy argument as I did, and that's totally all right in a physical sense. You can also try to calculate them, and the calculation is pretty similar to what we did in like 2 exercise sheets ago, for just the for just the expectation values of position and momentum for the Gaussian peaked at x0. Okay, so let's now go to the second exercise, which introduces these 2 notions of velocity for a wave packet, so which are phase and group velocities. And as we've seen in the previous exercise, when we are considering the evolution of the Gaussian packet, we see that under the free particle Hamiltonian, it moves along the x-axis in a particular way. And there are 2 velocities that we can distinguish for these types of wave packets. So first velocity is kind of the velocity of a wave packet as a whole. So for example, for the Gaussian wave packet, this will be the velocity of the peak of the Gaussian. So, or the velocity of the envelope function. So velocity of the envelope function, like, for example, velocity of the peak of the Gaussian. And this is called a group velocity. So imagine that we have some envelope function here, and then we have our wave packet, right? And then 2 different velocities. So the first one is for the wave packet as a whole. So like how, what is the velocity of the, yeah, of the peak of the envelope, we can say. and this is called a group velocity. However, one can also introduce a second notion of velocity, which would be the velocity of the particular phase in the wave packet. So you can think about it as a velocity of the crest of the wave. So not of the envelope in which the wave is confined to, but the crest of the wave. And this velocity, because it corresponds to the velocity of the particular phase, is of the wave packets. It's called phase velocity. So you can say that velocity of a crest of the wave, and this is called, so the first, this is called phase velocity. And the first one is called group velocity. So the group velocity refers more to the, again, as I said, to the movement of the envelope of the wave packet, while the velocity, the phase velocity, corresponds to the movement of the crest of the wave, like inside the wave packet, inside the envelope. And these two notions are different, and we'll see that the velocities that correspond to these two are also different. So to analyze this, we'll look at the general form of the wave packet, which can be written as psi of xt 1/2 pi h bar square root integral from -infinity to +infinity some function f of k, which determines the shape of the wave packet, e to the power ikx minus I omega of kt dk. So just so this is a general form for a wave packet, not necessarily Gaussian. Yeah, just to compare it to the example of the Gaussian that we had in a previous exercise. So if we look at the psi of xt that we got here, so here we have some coefficient, and then we have essentially yeah, this exponential which depends on k, and then the movement of the wave is e to the power ik is determined by e to the power ikx minus I h t h squared k squared over 2 mu, and here we have omega of k, and for this case we can write that the omega of k, so for Gaussian, for example, this function omega of k that appears in this definition is just yeah, h squared k squared over 2 mu h. Yeah, generally omega of k is the angular frequency, and omega of k is usually like just E of k, the energy, over h bar. Yeah. So this is just the definition of this angular velocity thing. And here we need to analyze the situation further, we need to make an assumption, which is that f of k, which determines the envelope, the shape of the envelope, is peaked around some value k equals k0, which again, another example of such an envelope is the Gaussian. And if it's peaked around k equals k0, then we kind of can only consider the integral that appears around k0. So we can just assume that it makes the largest contribution around this point k0. And so we need to write in terms of series everything that appears in the integrand as a series written around in the neighborhood of k0. So then we need to write omega of k as a series in the neighborhood of k0. So it's omega of k0, which we will call omega 0, plus the first derivative at k0, k minus k0, plus everything else. So we will not consider terms of the second order. So this we don't take into account. And then we can take psi of xt and then substitute omega of k. So this will be f of k. Then we will have the exponential of ikx minus I omega t minus I d omega by tk at k0, k minus k0 t, and other terms. So integrating over dk. Then we can take out e to the power I k0x minus omega 0 t. And what is left in the integrand is f of k, exponential of I k minus k0 x minus, let me write it first as d omega by dk at k0 t, and integrated over dk. And then we arrive to the following conclusion. So we can separate this this expression into two parts. So the first part would be e to the power I k0x minus omega t. So it's this part. And essentially, this is just a plane wave moving with the velocity omega 0 over k0. It's just a plane wave. And the second part is like this coefficient f of k, this exponential and this beast here is actually can be seen as just a wave pulse moving at velocity v, which is equal d omega by dk at k0, because we have this term appearing here. It's like x minus some velocity by t. Yeah, we can even write this wave pulse as just like wave pulse of x minus this vt. Okay, and since we can identify two velocities, so we can identify this psi of xt as a product of these two waves, which move at with different characteristic velocities. The first velocity is actually the velocity of the plane wave part is actually indeed the phase velocity. So it's just it just corresponds to how the crest of the wave moves within the envelope. So what is happening with the wave in the envelope. And the second part corresponds to the wave pulse, which is moving along x, and it corresponds to how the wave packet as a whole moves along x. So it corresponds to the velocity of the envelope, and this is exactly the group velocity. And so yeah, so the group velocity is usually just defined as the omega by dk at the point k0. Yeah, of course, one can argue that we can take higher terms in our decomposition of omega of k in the Taylor series for omega of k. But yeah, so but then this terms will give you a smaller contribution, essentially. And so this approximation is sort of only to the first order terms. Okay, so we identified what we mean by phase velocity for the wave packet and the group velocity. And now let us look at the example of the free particle. So, and for the example of the free particle, let us show what is the difference, that essentially that there is a difference between the values that we will get for the phase velocity and the group velocity. Okay, so let us first calculate the group velocity. So this is the omega by dk at k equals k0. Omega is the angular frequency, which is the energy over h bar dk, k equals 0. So at k equals k0. Then the energy depends on k in the following way. So it's h bar squared k squared over 2 mu h differentiated by dk at k0. Then, so we differentiate h bar over 2 mu by 2k at k0. We get h k0 over mu. So in other terms, for example, if we look at the Gaussian, then k0 hk0 corresponds to the expectation value of the momentum. So we can also write it as just the expectation value of the momentum over mu. Okay, this was the group velocity, which we kind of expected because we saw that for the Gaussian wave packet, which we evolved under the free particle Hamiltonian, kind of just to remind you, what we got for the Gaussian was that the expectation value of the position, which determines the peak of the Gaussian, would move with x0 plus hkt over mu. And essentially what we found here is this velocity, hk over mu. So indeed, like the Gaussian as a packet moves with the group velocity, which is hk over mu. Now let us look at the phase velocity. So the phase velocity is just what we identified as omega 0 over k0. And omega 0 is kind of E0 over h bar over k0. And this is h bar k0, h bar squared k0 squared over 2 mu h over k0. And what we get is hk0 over 2 mu, or yeah, the expectation value of the momentum over 2 mu. Okay, great. So this is a very good example which shows us that the phase velocity and the group velocity for a free particle are actually different velocities. And as a comment, the phase velocity is usually less than the group velocity. And if in some medium the phase velocity is bigger than the group velocity, then this medium is kind of anomalous with some refraction coefficient, which is usually anomalous, and the waves there behave a bit weird. But for the most of the mediums, and like here for vacuum, the phase velocity is less than the group velocity. Yeah, so these, but in any way, the idea is that these are two different notions which you can introduce for the wave packet. Okay, so this was the second exercise, and now finally we're coming to the third exercise, which is about the double slit experiment. So this exercise kind of combines the double slit experiment with some constructions that we learned about in the previous exercise class. So in the previous exercise class, we saw how to indirectly measure a system that we don't have access to. And for that, we needed the help of another system to which we coupled our system, our initial system, which we wanted to measure. And then we, with the help of an interaction Hamiltonian, which would indeed couple these two systems, we could just in the end measure the second system, and by that indirectly measure the first system. And here we'll first analyze this double slit experiment and then apply this technique to try to measure the particle after passing two slits. So essentially the setup that we have is, so we have our double slit. Let's give some coordinates. So this is x, 0. So the distance between slits is L. And then we have an electron, like a particle, which is passing through the slits. And then of course we analyze it with quantum mechanics. Maybe actually let me use a different color. Here, here. So we label this psi L, psi R, which correspond to the particle going through the left and right slit. Sorry, I just got a message. I'll just quickly check it. Oh, okay. So yeah, so we have this psi L and psi R, and yeah, so then we have this incoming electron, which is initially in the state, which we label as psi alpha, 1/2 psi L plus e to the power I alpha over √2 psi R. Yeah, and for in the position representation, it's just like psi L of x minus L equals psi R of x. So the idea is that kind of these two wave functions, psi L and psi R, they are identical, but they're just shifted one with respect to the other by the distance L. And we assume that psi L and psi R have support only in a small region. So the bracket of psi L with psi R equals 0. You can just imagine it as like if psi L is something like this. So it starts here, but it ends before the function kind of dies before L over 2, and with the psi R, same. I think it's not very symmetrical, but yeah, excuse my drawing. Yeah, so we just assume that they don't, these two wave functions, they don't overlap. And then what we will need are also two projectors, PL and PR. So PL is the integral from -infinity to L over 2 dx xx, and PR is identity minus PL, which will be just the integral from L over 2 to +infinity dx xx. Okay, so how do we understand this projector? So the first projector is just essentially the position projector, but only for the like left part here. So from -infinity to L over 2. And the second PR is the projector on the right side. So from L over 2 to +infinity. Okay. Now let us look at how the PL and PR act on the wave functions psi L and psi R. Well, first let us act on the psi L and see to what it corresponds to in the momentum representation. Sorry, in position representation. So we just substitute PL here, dx xx psi L. Sorry, so we need to integrate over x prime. Yeah. Then what we have here is integral from -infinity to L over 2 dx prime x prime x prime psi L equals so let us do it the right way. So it's integral from -infinity to L over 2 dx prime. Then the bracket of x with x prime, as we remember, is just a delta function, delta of x minus x prime. And then here we have x prime psi L. And x prime bracket x prime with ket psi L is psi L of x prime, just our psi L in the position representation. So we can write it here. Question is, can we already just kind of conclude that, oh, we just apply delta function and we get psi L of x? Well, that's not exactly correct, because the delta function definition that way only works if the integral is from -infinity to +infinity. So then we need to do that. Psi L of x prime delta of x minus x prime dx prime minus what we is left here is integral from L over 2 to +infinity psi L of x prime delta x minus x prime dx prime. So the first integral, as we remember, from the definition of the delta function gives us just psi L of x minus the second integral is actually 0 because psi L does not have support on the region from L over 2 to plus infinity. So it's just 0 there. So then we don't even care about the delta function. So it's going to be 0. So this is psi L of x. Which means that PL acting on psi L gives us back psi L. Like carrying out an analogous analysis, we can find out that psi L acting on psi R would be 0, simply because these two functions have different support in non-overlapping regions, actually. Then for the pi R acting on psi L, we'll also get 0 for the same, because of the same argument. And then with the pi R acting on psi R, we'll get just psi R back. Good. Then what happens is, let us come back to our setup of the experiment. So we have the double slit, we have the electron going in, then we have here psi L, psi R, and then we have a screen, right, in the end. And if we know that we would just see, what we will see is the interference pattern. However, what we can do also is right before the wave gets to the screen, we can try to measure. We can ask ourselves, okay, did the particle go through the right slit or through the left slit? And for this, we need to place some particle on the right side. We call it S. So we need to particle on the right side. And we describe this particle by its internal degree of freedom, which we denote as a state belonging to the Hilbert space HS. And we model it as a qubit, so as a two-level quantum system. And this particle has a property that it is sensitive to the presence of the electron. So essentially, if the electron goes through the right slit, then the state of the particle flips, and if it goes through the left slit, nothing happens. So essentially, what I mean is that, again, back to our double slit, is that if the electron goes here, then the state of this additional particle S, it flips. If it goes through the left slit, then nothing happens. So I'll just note it here that particle is sensitive to the presence of the electron. Okay, and we can describe this process of this condition, that if the electron goes through a right slit, this particle S flips. If it goes through the left slit, nothing happens. We can describe it as a following unitary, UXS, which is PL tensor product 1S. So it's like if So PL, as we remember, corresponds to the projection on the left side, and PR corresponds to the projection on the right side. And if it goes on the left side, nothing happens on the system S. If the electron goes on the right side, then the flip happens. The bit flip, as we remember, corresponds to the Pauli operator X. I'll just remind you that in the matrix form, it looks like this. So 0, 1, 1, 0. And let us kind of confirm for ourselves that indeed this unitary evolution acts in an appropriate way on our initial state. So our initial state is this electron in the state psi alpha. And the system S is initially in the 0 state. Okay, so what we get here is 1s plus PR xs acting on, let me maybe first write it as psi alpha by 0s. Then we can open the sum, and what we get is pi L psi alpha tensor product 0s, because it's just the identity acting on 0s, plus pi r psi alpha tensor product xs 0s, and this will be just 1s, right? Because the bit flip changes 0 state to 1. Okay, then let us consider the components of the sum separately. So let us first act with pi L on psi alpha. So pi will be pi L, 1 over square root of 2 psi L plus e to the power I alpha over square root of 2 psi r. We remember that acting with a pi L on a psi r does not give us anything, it gives us a 0. So the second term in the sum disappears. And the first term, pi L acting on psi L, just gives us psi L. So it'll be 1 over square root of 2 psi L. Then the same we do for the second component of the sum, which is pi r acting on psi alpha, be pi r acting on 1 over square root of 2 psi L plus e to the power I alpha over square root of 2 psi r. The first term does not survive. The second term gives us 1 to the power e to the power I alpha over square root of 2 psi r. Okay, so the final state then, let's label as like psi xs, gives us 1 over square root of 2 psi L tensor product 0s plus e to the power I alpha over square root of 2 psi r by 1s. And here we can see that indeed we did succeed to couple the kind of the state of the electron passing through the left slit or the right slit with the state of this particle S, which is just sensitive to the presence of the electron. So so we achieved that the final state between these two systems is a superposition between these two states. This one, and this one. And indeed, for example, if we measure the particle S, then we would also successfully measure whether the electron went through the left slit or through the right slit. Yeah, so if we measure the electron in state 0, then the state of the electron would then automatically collapse to psi L. And if we measure the particle S in state 1, then the state of the electron would automatically collapse to the psi R, so going through the right slit. And kind of the final part of the exercise is kind of connecting it to the previous exercise sheet. So the idea is that we indeed identify the unitary evolution which is needed to couple these two degrees of freedom. However, what we did not identify is the Hamiltonian under which we need to evolve these two systems for them to be evolved under this unitary evolution. So we just need to find the Hamiltonian hxs and time tau, let's call it, so that the evolution under this Hamiltonian for the time tau would correspond to the unitary evolution uxs. And so the final question is to find hxs, and of course, and tau corresponding. Of course, in the end, what you find out is just the hxs tau. And of course, hxs can be scaled and it's up to some coefficient. And as we've seen actually in the exercise sheet 3, I think we did prove that indeed for each unitary there exists an operator hxs such that we can write the unitary in this way. So it exists, we only need to find it. And I will not do the derivation here, but I'll just give you a hint that hxs would be some coefficient by pi r acting on the first system on the electron by rx of tau delta. So t over tau, function of tau delta, where delta is some coefficient and tau is the time under which we need to evolve the Hamiltonian. And Rx of theta corresponds to the rotation of the qubit around x-axis. So it's just e to the power minus I theta over 2x. And intuitively, you can see where this Hamiltonian is coming from. So this Hamiltonian, we know that the action of the unitary corresponds to doing nothing if the electron is going through the left slit, and flipping the system S, the state of the system S, if the electron is going through the right slit. So since we don't care about what happens with the with the situation when it goes through the left slit, we can leave it out in a Hamiltonian. And the Hamiltonian would then just correspond to the action which we do in case the electron goes through the right slit, hence the pi r projector acting on the first system. And the second, what happens with the second system? Well, what we need the Hamiltonian to achieve, we needed to fully rotate the state of the qubit from 0 to 1 at in the period of time tau. And this corresponds, of course, to if we evolve it from 0 to tau, then this rotation has to go from 0 to tau. So we just need to tweak. We just need to tweak the rotation so that this rotation would be complete in time tau. Okay, so I think yes. I think this is all exercises I wanted to talk about for today. So again, we looked at 3 exercises. The first one is we were analyzing the movement of the Gaussian wave packet under free particle Hamiltonian. Then in the second exercise, we looked at the 2 different notions of velocity for the wave packet, which are the group velocity and the phase velocity. And in the third exercise, we looked at how we can measure, in double slit experiment, how we can measure kind of through which slit the electron went through right after it went through the slits, by coupling it to another degree of freedom, which was modeled as a qubit, and finding the appropriate evolution for this case. Okay, so yeah, if there are any questions, please ask. Yeah, I think Lídia wanted me to remind you that, let me check again just to be sure. So she said that, I think she already announced it yesterday, maybe, or on Tuesday, but so the lecture won't be on Zoom today, but she's gonna upload it on YouTube sometime later in the day. So yeah, I think this is all for today. Yeah, I think there is a question. Ah, yeah, you're welcome. Yeah, then thank you. Have a nice, if there are no questions, then yeah, have a nice end of the week. See you next time.